The specific heat of a substance is the amount of heat required to raise the temperature of 1 gram of that substance by 1 degree Celsius. We also call this heat capacity. So far, we've been using the heat capacity of liquid water and solid water in our quantitative energy problems. But because different substances have different composition, we have different values for each of these substances for the specific heat. Okay? We've been using these two so far for liquid and solid water, but we can also see that we've got gaseous water and a variety of other common substances that we can use their heat capacities for. The amount of heat absorbed or released by a substance during a change in its temperature is not only dependent on its physical state, but it also depends on the mass of the substance, okay, which is why we have the grams in our heat capacity. Okay. So the example problems we're going to do right now are going to be almost exactly the same as what we've been doing on worksheets 3 and 4. The only difference is instead of using water, we're going to use a different substance. So let's take a look at our first example. If the temperature of 34.4 grams of ethanol increases from 25 degrees Celsius to 78.8 degrees Celsius, how much heat has been released or has been absorbed by the ethanol? So, first thing we want to take a look at is the fact that we have ethanol as our substance. If we look back up in our table, we can see the energy constant for ethanol specific heat is 2.44 joules per gram degree Celsius. I'm going to go ahead and write that down. Joules for 1 gram times 1 degree Celsius. Okay. We have our mass, but we can go ahead and find our change in temperature. So remember, this is going to be TF minus TI. So for us, that is 78.8 degrees Celsius minus 25.0 degrees Celsius for a difference of 53.8 degrees. Okay. Now that we have those pieces, we can set up our proportion same way as we did before with our water problems to find the amount of energy involved in that process. So we're going to use our 34.4 grams times our 53.8 degree temperature change. Okay, if I'm solving for x, let's cross multiply. X joules is going to be 2.44 joules for 1 gram going up 1 degree Celsius times 34.4 grams and 53.8 degrees Celsius. You can go ahead and get rid of the units. Grams cancel, degrees Celsius cancel, and now all we do is multiply. 2.44 times 34.4 times 53.8. Okay. Again, we want reasonable number of sig figs here. Let's go ahead and go with 3. So I'm going to round this 4,515.7568 joules down to 3 sig figs. So let's make that 4520 joules. Okay. Again, exactly the same as the problems that we've been doing, except for we're not just using water as our substance. Okay, let's do another. A 4.5 gram nugget of pure gold absorbed 276 joules of heat. What is the final temperature of the gold? The initial temperature was 25, and the specific heat of gold, we're told, is 0.129 joules per gram degree Celsius. And so here, we're just having that change in temperature. The difference in this problem is that we're going to be looking for just the change in temperature and then the final temperature. So let's use our energy constant. 0.129 joules for 1 gram times 1 degree Celsius. And we can plug in on the other side the 276 joules of energy that are absorbed, our mass of 4.50 grams, and we're going to look for delta T. Okay. We can cross multiply to get the 4.5 and the delta T out of the bottom. Okay, so we'll go ahead and do that. Thanks. I'm going to wind up with the 0.129 joules for 1 gram times 1 degree Celsius times 4.50 grams, and delta T equals 276 joules. To get delta T by itself, divide both sides by our constant, and 4.50 grams. And then we can worry about our units. So, both of those go away on that side. Joules cancel, grams cancel, and we're left with degrees Celsius. Okay? So time to do our math. Delta T is going to be 276 divided by 0.129 divided by 4.5. So that gives us 475 degrees Celsius as our change in temperature. If we want to find the final temperature, we're going to take our change in temperature plus the initial temperature. So we want to take that 475 we just calculated plus 25 to start out with for a final temperature of 500 degrees Celsius. Now, the main way that we measure heat in the lab is using a process called calorimetry, where we use a device called a calorimeter to measure the heat that's transferred. A calorimeter is just an insulated device that's used to measure the amount of heat absorbed or released during a chemical reaction or a physical process. In this, a known amount of water is usually placed inside an insulated container in our calorimeter, and that's used to measure the energy that is either released from the system or the water is used to provide energy absorbed by the system. Now, this is what we used in the lab last class. The calorimeter was not anything special. Remember, we just used a styrofoam cup inside a styrofoam container with a cardboard lid on top. And what we can use this for in the lab is to find the amount of energy. We can find the specific heat of an unknown metal. Okay, we could find final temperature. And we're going to look at a few different examples of how we can do these problems. Again, these are going to be very similar to what we did on worksheets 3 and 4 and on the first part of these notes, just using different substances. So if we're going to use this calorimetry to figure out a specific heat of a metal, we're going to do this just a little bit differently because we're going to be calculating the energy constant. So let's look at our first example here. A piece of metal with a mass of 4.68 grams absorbs 256 joules of heat when the temperature increases by 182 degrees Celsius. What is the specific heat of the metal? And then the second part of this is referencing a textbook, which we don't have, so we're not going to worry about what that metal actually is. Okay, so if you think about those heat capacities or the specific heats that we have in the table on the other page, all of those are measured in the same units, which are joules for every 1 gram times 1 degree Celsius. And you're finding the number of joules. Okay? So for us, if we want to find that specific heat, that's exactly what we're going to do, is find that X joules in the energy constant. But this time we're using our data to do that. So we're going to plug everything in the same spots. 256 joules are used with 4.68 grams of our substance, and the temperature goes up 182 degrees Celsius. And that's it. Divide. Okay, 256 divided by 4.68 divided by 182. And that's going to give us 0.301. And again, our units are joules for 1 gram and 1 degree Celsius. Okay. Simple. Okay. Now we can, like I said, use calorimetry to find energy. We can also use it to find final temperature. We'll do that. This will be the last example that we look at. Okay. If 335 grams of water at 65.5 degrees loses 9,750 joules of heat, what is the final temperature? Okay, now, the word loses is really important because that tells us the energy is going out of the system. So this is going to be a negative value when we plug it into our energy constant. Okay. We have water in the liquid form, and so we're going to use the energy constant for that, which we've been using quite a bit, 4.18 joules for 1 gram, going up 1 degree Celsius. Okay, so we're going to find a delta T. But again, the big difference here is that we want to use a negative amount of joules, and that's 9,750 joules, because the energy is going out of the system. It's being lost. And everything else is going to be the same from this point on. 335 grams, and we're going to find delta T. Okay. Do a little math. 4.18 joules, 1 gram, 1 degree Celsius. We're going to multiply the 335 grams and the delta T to get them out of the bottom and set that equal to our energy in joules. Move this up here. Okay. Divide both sides by 4.18 joules per gram degree Celsius and 335 grams. 4.18 joules, 1 gram, 1 degree Celsius, and 335 grams. Okay. That cancels, joules cancel, grams cancel. It's getting a little messy, so let me rewrite this. Delta T is going to equal negative 9750 joules over 4.18 joules per 1 gram, 1 degree Celsius, times 335 grams. Okay. Do our math. Negative 9,750 joules divided by 4.18 divided by 335 should give us a negative number. Okay, this will be negative 6.96 degrees Celsius. Okay, again, we're finding final temperature. So we're going to take that change in temperature plus the initial temperature. Okay. To get our final, initial temperature is 65.5 degrees. Final answer, 58.5 degrees Celsius, which makes sense since the energy left the system. Okay. Now, this last example that we have here, we'll look at together as a little bit of a review in class on Friday. But now that you know how to do these problems using different substances and their energy constants, go back and take a look at your lab And you should be able to find the energy that's released to the water from your piece of metal, whether it was aluminum or brass.